I'm going to introduce our project presented on your opportunity 5, which is Hawaii Hierarchical Visual Knowledge Transfer for Efficient Vision Language Models. So here, vision language model, we specifically refer to multimodal large models, also as known as generative vision language models. Okay, first thing will be the background. So yeah, a general background on large models. So large models are trained on a large amount of text data, and large model is able to generate text based on the text inputs. So based on a lot of researcher and findings, we found out that large models are able to learn that kind of world knowledge, general knowledge, common sense knowledge from a very big set of training data. And as for generative vision language models and multimodal large models, we want to do here, instead of training a model from scratch, we want to utilize the knowledge already encoded in the large model parameters to understand the multimodal world. So here, usually we have image, video, and audio, a lot of data from different modalities as input. We have modalities, specific encoders, and projectors to get embedding that larger models can understand. And we can generate text based on the multimodal inputs or generate other data like image, video, audio based on using some projectors and generators. So usually the larger model backbone will be an autoregressive model. And for modality specific encoder, that will be based on like the characteristic of different modality of data. So for image, we usually still use transformer, video also transformer, but audio maybe like other frequency-based encoders. And yeah, by connecting large models with multimodal data, with modality-specific encoders and projectors, generators, and the multimodal data is also like able to be understood using text. Okay, so the problem we investigate in this project is that for vision encoder, we usually use clip, and we know that a clip is very small because usually the clip we use, the version of clip we use, the transformer-based clip, and it is only like 87 million of parameters for clip, and it's much smaller than large models, which usually maybe at least 2 or 3 billion. And it could be up to 100 million or 300 billions. So, and also clip is only pre-trained on image level contrastive learning, and the learned representation are kind of coarse-grained, a little bit weak compared to large model learned. So the visual tokens usually not quite informative. And to solve this problem, current researchers, they want to say, okay, since clip is train on a small set of data, and also the parameter is small, can we incorporate more pre-trained visual encoders to have a more informative visual tokens? So what they did is just take an example. We can introduce Sam and Eva which are two pre-trained visual models on Sam and detection. Thanks. So Sam is pre-trained on segmentation, and Eva 2 is pre-trained on detection. And still we have some projectors, but I remove here for simplicity. We get the visual tokens by Sam and visual tokens by Eva. They have the same shape N by D, and is the number of patches, and D is usually the feature dimensions, which usually are different, but we just for simplicity, we set it to the same here. So usually we can do channel-wise concatenations, and in this way we can get a 2n by 2d fused tokens, or maybe sequence concatenation, and we get fused tokens of the shape of 2n by d. And those fused tokens will be input to a large model for understanding, because here we introduce like at least Sam and Eva, the combined version, they have more parameters and they are pre-trained on more data. So the capacity of that model are usually bigger than clip only. And in this paradigm, people are already using 4 more here, maybe sum, eval, comnex, and pixel to struct. The advantage of this paradigm is we get very good performance as evidenced by already published papers, Eagle and Leo, our paper. And we also get domain level knowledge, like SAM is on segmentation, EVA detection, comnex is on classification, and tabular data we have pixel to struct. But yeah, in this way, you can get visual tokens, very informative. But just as my previous project is like the problem previous project is working on is in this way, we're gonna have a very large number of visual tokens that will be pretty slow training and for inference, though the visual tokens are informative. So recently people are thinking about, can we do knowledge distillation or other methods to use only one visual encoders to mimic the behavior of multiple visual encoder? And there's one example, MoveKD, published on CPR 2025. So we're still gonna use 2 teachers as example, simplicity here for simplicity. So keep visual encoder, keep frozen, and we have 2 teachers here, like one is SAM, one is eval2, and we get the visual tokens generated by 2 teacher and clip. So what they did is they minimize the MSE loss between the visual tokens, teachers' visual tokens and student visual tokens. And then they add LoRa adapters, clips visual encoder, so that the knowledge of SAM and eval will be fused into the LoRa adapters. So yeah, in that way, somehow clip has more capacity because first we got more parameters by adding LoRa adapters, and also the LoRa adapters is fine-tuned on the MS loss, like learning the knowledge from EVA and SAM, those 2 very informative, very useful teacher, so that we could get better results. And yeah, other parts, the learning paradigm are the same. So we have large language model, it is fine-tuned, and input text instruction, and we finally get a response. And the SAM and EVA, those 2 teachers are only used during the training. And for inference, we only still have clip only, and also a very small set of LoRa adapters, so that we don't need to run multiple visual encoders during inference. At least for inference, our efficiency could be improved. But yeah, there's still problem. So this is a problem we actually investigate in this project. So we found that actually using a fixed set of adapters for learning from multiple teachers that is not useful. That is not possible because SAM and EVA, they are trained on different data sets. They are trained on different like task, segmentation, and detection. So the prior they learn from those data and tasks are different, and they might be conflicting with each other. And that domain and expert knowledge might be compromised because we just combine all the knowledge and put into a fixed set of LoRa adapters. So they'll be mixing with each other. That means the domain level knowledge will be lost. So in this project, our goal is just in 2 folds. First, we want to keep expert level visual capabilities, addressing the problem of MoveKD. And the second goal is we want to using KD to reduce the computational requirements, so that is it possible for us to run only maybe clip so that we could get improved efficiency. And our solution is we want to have a hierarchical knowledge distillation here to improve the efficiency and reach our goal, like expert level visual capabilities. So first, there's gonna be a high level knowledge overview of our HKD, hierarchical knowledge distillation. I still use 2 teachers as example here. We have 2 visual teachers, teacher 1 and teacher 2, and 1 single clip encoder, which serve as our student using inference. And we have fine-grained knowledge distillation. The goal is to learn teacher-specific knowledge distillation. We also have coarse-grained knowledge distillation, which targets at general knowledge transfer. And for fine-grained distillation, we introduce a set of teacher-specific adapter. And for each teacher-specific adapter, they only learn knowledge from one teacher. Like teacher specific that adapter 1 only learn knowledge from teacher 1, and that adapter 2 only learn knowledge from teacher 2, so that the conflict between different teachers, the conflict between different priors, the learning distribution will not be interfering with each other. That could be give us like a clean, less noisy knowledge transfer. But we also we also cherish the common knowledge, the common sense between among multiple teachers. So this is the reason why also still incorporate coarse-grained distillation. So here in coarse-grained knowledge distillation, we summarize the knowledge from teacher 1 and teacher 2, and then transfer it to a set of general adapters, which is just what MoveKD did, but we have a little bit different design here. So all the adapters, they are LoRa-based adapters, and we're gonna just put them on the single clip encoder so that clip can be seen as equipped with teacher's specific domain knowledge. And others keeps the same. We still have the same paradigm, like image put into output, images are put into the clip encoder, and we get the visual tokens, the embeddings. Embeddings will be put into large language models along with instructions, and we get a text-based response. Okay, that's all be the details of our model, because the previous one is just an overview. So yeah, with this, that will be the detail of our model. We have image and vision encoder, which is just clip, and we use transformer-based clip. So which means clip will have multiple layer of transformer layer. And for each transformer layer block, we have self-attention, add a norm, feed-forward network, and add a norm. And MOLA, mixture of LoRa adapters here, is just what we introduced for this paradigm. And yeah, then we get visual features which are put into large model with instructions, and then we get a response. So MOLA has general adapters, which are in blue on the bottom right. We have a set of general adapters and also a general router, so that during inference they can be selected based on the hidden state of the current layer. And the goal of general adapters are to learn common knowledge between all the teachers, among all the teachers and all the training data. And we also have teacher-specific adapters here on the bottom right in purple. So the same, we have teacher router and a set of teacher adapters. So the goal of them are to learn domain expert level knowledge. Yeah, this is a design of our architecture. And how about the training algorithm? So the first, I'll introduce the coarse-grained knowledge distillation, because yeah, that'll be simpler. So during coarse-grained knowledge distillation transfer, only general router and general adapters are activated. And for teacher-specific adapters, they are just deactivated during that process. And still we have two teachers here. We generate teacher 1 feature and teacher 2 feature when we do channel-wise concatenation and apply MLP to map them to have the same shape with the student visual features here. Then we minimize the MSE loss. So the goal here is it possible for us to summarize the knowledge from teacher 1 and teacher 2 by channel-wise concatenation? Yeah, this is just a goal. So the summarized features are served as general knowledge, and general adapters are activated by the router, and the router's input is just current hidden state by the output of add and norm here in the transform block. And teacher adapters are detached because we only want the knowledge be transferred into general adapters. Okay, next is for fine-grained KD. For fine-grained knowledge distillation, yeah, we activate teacher-specific adapters one by one. So first, we only activate teacher adapter 1 like at each layer so that we could seen as clip plus very pure teacher 1's knowledge. And then we get a student 1 feature and we minimize the MS loss between teacher 1 feature and student 1 features. Yeah, we only activate teacher 1 adapters. Please remember this detail. And this is a very special design. So, and then we only activated the second teacher adapter so that could be seen like we only utilize the knowledge from teacher 2 and no other teacher's knowledge is incorporated in this process, feed-forward process. And then we generate student 2 features and we minimize the MS loss between student 1 feature and teacher 1 features to transfer the knowledge of teacher 2 to this adapter only. This is like how we did for fine-grained knowledge distillation. So that because for each feed-forward process, we only activated 1 adapter, in essence, the knowledge will be conflicting with each other because there's only 1 adapter is activated, and the gradient will only flow back to 1 adapter. Okay, so the domain or expert level knowledge is transferred to a specific adapter instead of a set of adapters shared by a lot of teachers. And general adapters are detached or deactivated. And only the corresponding teacher adapter is activated during this feed-forward or backward procedure. So yeah, that's basically everything about our model. The final thing will be just training loss. So training loss will be the sum of test generation loss. Second one is the MSE loss. And third one is the mixture of experts balance loss because we are using multiple adapters. So the text generation loss is just minimizing, maximizing the probability of generating the corresponding like ground truth token given the previous tokens and also the model's parameters. So for example, let's have an example here. If we're generating a sequence like I am a student, and I'm a student, the final word, that will be the teeth word. So like given I am a, that previous t minus 1 tokens, and also models parameters, we want to maximize the probability of generating student that token only. And the next loss will be just MSE loss we introduced in the previous slides. The last loss is mixture of experts balance loss because we have multiple LoRa adapters. We want to all the adapters are kind of equally activated so that the capacity could be the added adapters could be fully utilized and like all the parameters could be utilized. So this loss is just minimizing that function. So n is the number of all the adapters, and if I is the fraction of tokens routed to the i's adapter, and pi is the mean probability of that adapters assigned by the router. So overall, we wanna have that true fraction assigned to the adapters, and the mean probability of assigned to that that adapters is equally distributed between all the adapters so that this sum will be minimized. Okay, this is an overview of our experimental results. So as for the efficiency set, we only use 40% of GPU time and 30% of flops compared to our baseline ego. And we have improved performance on 3 representative benchmark datasets, MME, MMU, and VSwiss. And also we have that visualization to see how good is our model routed between different teachers specific adapters, because the reason we are incorporating multiple teachers and multiple teacher adapters here is the model is able to utilize the knowledge from different domains. So This blue ones refers to clip, like general knowledge. Orange one or yellow one refers to EVA, activated or activating EVA. EVA is string detection. A little bit fine-grained knowledge. Complex is on image classification. So still a general knowledge. So we can see on MME, they usually, and C bench, because they are like general, kind of general knowledge. So they tends to activate EVA and complex only. And for MMU, different here is they usually activate a clip all the time, but they still select EVA and complex as complementary, like second choices across different layer. So we do see that for different benchmark data sets, different experts like are suitable. So like different experts are different, right? The best suitable adapters are different for each data set. So yeah, that's the reason we want to do that. So this visualization actually prove our idea. Takeaways we can get is like hierarchical distillation is very useful from coarse-grained to fine-grained understanding. And also like distilling multiple vision experts into one encoder is also useful on efficiency side and effectiveness side. Yeah, but still there are some limitations. We only distill knowledge from a fixed set of visual data. And what if we are deploying our model into like medical data and remote sensing data and autonomous driving data, or maybe we're deploying the driving models in different countries. Maybe like we train the model in Canada, but what if does it still work? Will it still work in Europe or China or Japan? So that will be something we want to think about. And second limitation is we only distill knowledge on visual encoders, and we don't care about large models right now. And also this project and last project only focus on image. So corresponds to this three limitations. The first one I want to say maybe it's possible for us to adaptively add and remove teachers upon requirements of test data. So something already did by previous research is RAG. Like we can retrieve medical data if we're deploying model in medical scenario. But what if like, is there any other solutions and we don't want to do RAG? Can we just add more teachers and add some visual encoders without any training, or maybe just during test time adaptation? Would that be possible? And for the second limitation is, yeah, pretty straightforward. We should do knowledge distillation on LLM as well. We can have the knowledge from multiple sources like Queen, DeepSeek, Llama, and for the final limitation will be we can extend our model to video point clouds and more modalities, for example, audio as well. That could be useful. Okay, that's everything for my presentation, and thank you all for joining this session.